In the remainder of this chapter, we are going to say some words about isomorphisms of fields, which we're going to define presently and are basically exactly what you think they are. And then it turns out that using what we've learned about fields, we can kind of give a little bit of a gauntlet of relatively easy to prove theorems, which give us quite a bit of structure out of this concept. So let's start as we always do when we encounter a new concept and give it a mathematically precise definition. An isomorphism of fields is a bijective function. We could call it phi. How about f1 to f2 with var phi? I don't know. Should I say var phi out loud? That seems like it's cringe. It's for teching, right? Phi of a plus b. And also phi of AB equals phi of A, phi of B. So in other words, it's just a bijective function which preserves the operations in a field. Just like a group isomorphism preserved the notions of group multiplication, sent one group operation to another. This one, we got two operations. Field isomorphism preserves them both. Real easy stuff to see. Corollaries. And they're not even corollaries. How could they be corollaries? Because there's no theorem. Simple observations. Phi of 0 is 0. Phi of 1 is 1. Phi of A inverse is phi of A inverse. And phi of negative A equals negative phi of A. Why are all these things true? Because their proofs are exactly the same as for groups. When you're talking about additive properties, you just remember that a field is an additive group and you do the group stuff. When you're talking about multiplicative properties, you remember that if you take away 0, what remains is a multiplicative group. You apply the group properties. Great. What we want to know is, how does our concept of field extension interact with the concept of isomorphism? And so we can speak of extending isomorphisms. And here, Pinter introduces a little bit of curse notation. I'm going to do my best to follow this notation because I don't want it to even be more confusing by trying to switch it up on you guys. But what can I say? I find this notation to be confusing. So here's the situation. He says we have two fields, F1 and F2, and he calls an isomorphism between them H. And then he says we have two more fields, K1 and K2, which contain the Fs. And then he says we have another isomorphism, and he seems to use, like, in my printing of the book, it looks like it's italicized or something, and also maybe overlined, like fancy H bar. I'm going to try to stick to that notation. We have an isomorphism K1 to K2 with this H bar. And what he tells us is we will say that H bar extends H to mean H bar is an isomorphism, so it has those above properties, and also H of X equals H of X for X in F1. And so, in other words, it's an extension because the restriction of cursive H bar down to F1 agrees with ordinary H, right? So that should match your intuition for what it means to extend a function. Now, if you have an isomorphism already, how should I say this? I don't want to, okay, never mind. I want to keep that in a thought bubble because I don't want to talk about things that aren't fields. Pinter has a little bit of discussion following this section about polynomial rings and integral domains and so on. Um, I don't want to talk about that stuff because we didn't talk about that stuff. I do want to make one comment, which is when you have any kind of isomorphism of fields, whether it's the little h or the big H or the fancy H, it doesn't matter. An important observation is isomorphisms of fields in general. Um, Actually, what I'm saying doesn't make any sense to talk about isomorphisms of fields and then talk about polynomials. So I think I'm going to have to. Hmm, how do I express this comment to you guys without going into an entire tangent on rings? Um, we will simply define an extension of a field isomorphism to a polynomial isomorphism. And I'm not going to worry about what the heck I'm like, if this is agreeing exactly with Pinter or not, because it's going to work, it's fine. Um, what this means is if I have a polynomial sum a I x to the I, right? This is a polynomial. And let's say H is an isomorphism F1 to F2. Then I will define a H bar of such a polynomial to be the sum um, now with normal H AI x to the I. And the idea here, and the reason I'm allowed to get away with making up whatever I want seemingly and having it be okay, is if if it made sense to extend this to the polynomial also, then I would be forced to say something about what um, H does to a power of X. And what I'm essentially saying is just don't do anything to them. Because since it's a homomorphism, right, we know it's supposed to be multiplicative, right? And so on any given monomial, right, you have an AI x to the I, you get this H of AI, right, the normal H, because AI is a field element. And then you get this. And because it's a homomorphism and continues to be multiplicative, I can put that I outside. And so what I'm saying is that we should do is we should define the fancy H of X to just be X. And then we're going to just let it roll from there. And it turns out that this is fine, right? Nothing breaks when we do this. And the reason I got started talking about this is because what it means is that this preserves isomorphisms. Or sorry, it preserves irreducibility. What am I trying to say? Getting late. Preserves factorizations or irreducibility because it has to, right? If it's a multiplicative thing and one of them factors and you apply an isomorphism, the multiplication of the factorization has to go over to the multiplication somewhere. And so you could never possibly send something reducible to irreducible or vice versa because the inverse of an isomorphism is also an isomorphism. Okay. Properly speaking, you can fix what I'm saying if you want to take a little like 3 or 4 week tangent into the theory of rings, but I don't want to do that. Neither do you guys. We're trying to get to the good stuff here. So let me give the next theorem. This is theorem 3 in this section of Pinter. He tells us we have an isomorphism F1 to F2 and P of X irreducible in F1 adjoin X. we suppose that A is a root of P of X. So maybe I could just write P of A equals 0. And, oh yeah, there's this other piece of curse notation. If this polynomial is called A of X, maybe I'm calling it such specifically because of the AIs, he calls this polynomial HA of X to signify to you that he has, applied this change of coefficients, right? That's the idea here, that the H is an isomorphism. He's applying H to the coefficients, and the X's are just staying put. Okay. Curse notation. A is a root of P of X, and B is a root of HP. So in other words, I apply this change of coefficients along this map H. I get a new polynomial because all the coefficients are sent over there. P is then formally changed over, and B is some root. This is the setup. And what he tells us is then H can be extended to an isomorphism H bar, which takes F1 adjoin A to F2 adjoin B. And in particular, if you do this, H bar of A will be equal to B. Okay. The proof of this fact is not so bad. Essentially, we're going to unravel all the definitions of the things that we're talking about with this notation. So to start with, what are the elements of F1 of A? Those are polynomials in powers of A. And so I get something like C0 plus C1A plus C2A squared and so on up to some CNAN. This is what it means to be an element of F1 of A. All the C's, those guys live in F1. And similarly with F2. Maybe I can squeeze this in over here, right? We could have like a D0 plus D1B plus D2B squared and so on, DN, BN, live in F2 of B. The D's all live in F2, they're powers of B. The degrees are the same, they're both N because I have an isomorphism, right? So they have the same degree. Okay, well, now what I'm going to do is we're going to let H bar act on the coefficients, right? Let's just try to see, we define H bar of this mess. Well, what is it going to do, right? It's going to respect the A's in the same way as above and distribute over addition and multiplication. So we get H bar of C0 plus H bar of C1 times, we'll send that over to B plus H bar of C2, B squared, right? We're just breaking everything up over addition and multiplication. The A's are going to the B's. What we have to do is we would have to see, I guess I didn't quite finish, H bar dn b to the n. We're really squeezing it in there at the end. I don't think it really fits. Kind of fits if I scooch over a little bit. All right. In any case, this is how this is defined. And then we have to check that H bar is an isomorphism of fields. And basically Pinter gives like some sketch in the exercises. I could say a few words too. It satisfies the isomorphism equations that we required at the top because I forced it to, right? I started with H bar, or with normal H, being an isomorphism of fields. And I just insist that since you respect the addition and multiplication of the polynomials, those are the only two ways to add and multiply things, right? You could have field elements and you could have polynomial stuff. And so I've demanded that it satisfy the polynomial stuff. I suppose I have to check that it's bijective, but again, it kind of has to be because along the normal constants, I'm using an isomorphism of fields already. And so sending polynomials to polynomials is also kind of trivial. And so in that, for all these reasons, this is essentially forced to be an isomorphism. And I've mapped the polynomial p exactly onto its counterpart, hp. And so therefore, I cannot possibly be introducing any sort of new stuff, right? Like whatever the relations are, for example, the group addition and multiplication tables for the field operations, we saw in a previous exercise how those polynomials work when I'm like multiplying and canceling higher degree powers. Well, since I'm sending p exactly over to hp, it's got to be an isomorphism because of how this thing is concocted. And so we're kind of done. I understand this result seems a little bit maybe silly, but there is a very important special case. This is Pinter's theorem 4, which I think will hopefully add a little bit of clarity. The special case in question is F1 and F2 are the same field. And the original H between them, therefore, is F1 to F1, is just the identity. Let's state the theorem again now. Suppose that A and B are roots of what polynomial? Well, A was the root of P, B was the root of HP. But since this is the identity map, and this is it's not the identity, but they're the same field, and the isomorphism is the identity map, HP is just P again. So they are the roots of the same polynomial. Okay? Then there is an isomorphism, which he calls G, FA to F of B, such that G of X equals X for, I stopped writing the ones. I guess I could just erase those. That seems the easiest thing to fix. For X in F, G of A equals B. Okay, I think this is probably getting close to a good place to stop again. The point is, this allows me, we're moving in the direction of what are called field automorphisms, just like for group automorphisms. And so what this tells me here is that really all that matters is the polynomial, right? Upshot. All that matters is the irreducible polynomial. Because the roots are then all distinct from what we saw last time. And if you ever need to do a calculation where you choose a different root, there would be an isomorphism between the situations. So just to like really make this concrete, because I feel like what I'm saying is got to be descending into word salad. When we think about things like Q adjoin square root of 2, right? Things of the form A plus B square root of 2. The minimal polynomial of this is x squared minus 2, which has solutions plus and minus square root of 2. And I know that we probably point that out to our students all the time. So the point is, when you're treating x as either positive square root of 2 or negative square root of 2, it doesn't matter. There's always going to be a field isomorphism that would get you to the other one, namely Q adjoin negative square root of 2. And how would that isomorphism go? It's the identity along the base field, right? So along the original Q, it sends 1 to 1. And then we just send square root of 2 to minus square root of 2 and make it compatible with addition and multiplication. I'll just say with the operations. And when you do that, there's no calculation that you can perform in this field that could ever do anything meaningfully different from this field. In a sense, they're simply mirror images of each other. And that's all there is to it. All right. There's still more to this gauntlet of little theorems. So I think we'll stop here and we'll pick it up in the next one. See you in a bit.